Okay, and so this lecture we're going to talk about Taylor's theorem, and this will open up new worlds to us. It's useful in many ways. Let's get started. So first off, let's suppose we have a function f that's just expressed as a power series a0 plus a1 times x minus a plus a2 x minus a squared plus a3 x minus a cubed. Okay. If we evaluate that with x equal a, these higher order terms fall out and we're left with a0 being equal to f of a. Okay. Now we take the derivative of f, pretend that we can take it term by term. In that case, we've got f prime of x is equal to a1 plus 2 times a2 times x minus a, etc. So if we again let x be equal to a, we get f prime is equal to a1. Okay. If we continue in this way, we can see that the nth derivative of f evaluated at x is n factorial times a n plus n factorial a n minus 1 times x, etc. So that when I evaluate x equal to a and solve, I get that a n is equal to the nth derivative of f evaluated at a over n factorial. And so from this, okay, we see that f of x is equal to f of a plus f prime of x minus a plus f double prime of x, f double prime of a over 2 factorial times x minus a squared, etc. Now, at this point, we've not proven anything, okay? Because how do you know you can take a derivative of an infinite series, huh? But what we've got some motivation for the formulas on the next page. So let's take a look. All right. Taylor polynomial and the remainder. Okay, so we'll define p sub negative 1 of x to be equal to 0 and p sub n of x to be f of a plus f prime of a x minus a plus dot 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 f, and this there should be parentheses around this, the nth derivative of f evaluated at a over n factorial times x minus a to the nth power. Okay, we will refer to Pn as the Taylor interpolating polynomial of degree n. Okay, now let r sub n of x be equal to f of x minus p sub n of x and call it the nth remainder of the Taylor polynomial. Okay. Okay, one thing you'll want to put in your pocket is that r sub negative 1 is just the function. Okay, let's go on now to the next page and do some preparation before we prove our theorem. We'll do a calculation. Given the function f of x, we will find the Taylor interpolating polynomial of its derivative, f prime of x. Okay. Note that f prime of x evaluated at a is f prime of a. Yeah, duh. We can easily see that f prime, the derivative taken n times, is f n plus to the n plus 1, or derivative n plus 1, so that the nth derivative of f prime is the n plus first derivative of f. Okay. Now, therefore, if q sub n is the nth order Taylor polynomial of f prime, q sub n is equal to f prime of a plus f double prime of a times x minus a plus dot 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 the nth derivative of f evaluated at a divided by n factorial all times x minus a to the nth. Okay. So q, so if we take q sub n minus 1, it's everything but that last term. We'll just drop the last term and stop it here. So it's an easy observation, okay, that q sub n minus 1 is equal to p sub n prime. Okay, just go and calculate p sub n and take its derivative. They're the same thing. Okay, now we go to our theorem, Taylor's theorem. Suppose that f has a continuous n plus first derivative in the interval closed AB, and so that n plus first derivative is bounded between little m and big M on the interval AB. Okay. Then for any x between AB, the remainder, okay, is going to be, okay, little m divided by n factorial times x minus a to the n minus first over, which is, okay, so the remainder is between this on the little n and the big M over n factorial, x minus a to the n plus first on the top end. Okay. The important thing to note here is that, you know, for m, say if our m's aren't too big, okay, if they're fixed numbers, which, you know, okay, they will be, and x is close to a, then when n gets bigger, okay, this remainder is going to get smaller. All right. So we're going to now prove this by induction. Start off with the case n equals -1. Okay. In this case, the statement of the theorem is that m is less than r sub -1 of x is less than or equal to capital M. But since r sub -1 of x is equal to f of x, we're done by the definition of of little m and capital M. Okay. Okay, now let's do the induction step. For n greater than or equal to 0, we have that f of x is equal to p sub n of x plus r sub n of x. We take the derivative of f prime, and so it's equal to p sub n prime of x plus r sub n prime of x. It's easy to see from the discussion before the theorem that p n prime is a Taylor polynomial of order n minus 1 of f prime of x. Therefore, by induction, we have our remainder between m over n factorial times x minus a to the nth and capital M over n factorial x minus a to the nth. Okay. Now observe here that if I take the derivative of x minus a to the n plus first divided by n plus 1 factorial, that I get 1 over n x minus a to the nth power. Okay. By a previous result, okay, it follows that my remainder then is going to be between these two values as before, and this ends the proof.